If you're in the shower and someone flushes the toilet downstairs, you don't wait for the water to turn freezing cold before you reach for the handle. You anticipate the pressure drop and adjust the faucet immediately. In a process plant, a single-loop heat exchanger tries to do the same thing, but it operates blind. It watches the product temperature, our primary process variable, or PV, and adjusts a steam supply valve, the manipulated variable, to keep that temperature on target. But watch what happens when a process disturbance hits. If the main plant steam header pressure suddenly drops, the heat energy flowing into our exchanger plummets. And yet the steam valve doesn't move a millimeter. The controller doesn't know the steam pressure dropped. It only knows temperature. Because of the thermal capacitance of the fluid and the metal, it takes minutes before the product temperature actually slowly falls into the red. Only then does the controller finally wake up and tell the valve to open. By the time the controller reacts, off-spec product is already heading downstream. When a disturbance strikes a process variable with heavy lag, a single-loop control system is completely defenseless against the delay. To fix this, we need a way to feel that disturbance the moment it arrives, long before it has time to affect the final temperature. We do this by adding a secondary process variable. In this case, we install a flow sensor directly on the steam line, right upstream of our control valve. You can't pick any sensor for this. A valid secondary variable has to follow strict rules. It must manipulate the exact same steam valve. It must be hit by the exact same pressure disturbance. Its response time must be dramatically faster than the slow main tank. Wiring this flow sensor to a dedicated flow controller builds a rapid-fire feedback loop, nested entirely inside the slower primary temperature loop. This nested architecture acts like a shield. The fast inner loop traps and corrects flow disturbances immediately, keeping the slow outer loop completely isolated. But adding a second controller creates a hierarchy problem. The primary temperature controller can no longer communicate directly with the steam valve. The controllers must talk. The primary's output, its OP, becomes the secondary's live set point. But wiring isn't enough. The secondary controller can't stay in auto mode, which waits for human input. It must switch to cascade, or CASC, to accept the primary signals. You can run all the copper wire you want, but without that digital handshake in cascade mode, the two loops are completely disconnected. Let's test this logic. Here is a PNID for a distillation column reboiler. We have a bottom liquid level sensor and a steam flow sensor. Take 5 seconds. Which one is the primary PV and which is the secondary? Remember the rules of capacitance and lag. The steam flow reacts to a valve change in seconds, making it our fast secondary PV. The column level is a massive liquid capacity that takes minutes to change. That makes it our slow primary PV. The rule of cascade design never changes. You always nest the fast, highly responsive variable inside the slow, high-capacity variable. Let's put our completed heat exchanger system to the test. This chart shows our process running perfectly at steady state across 3 variables. Watch what happens when that massive plant steam pressure drop hits us again. The pressure drops sharply. In a fraction of a second, the secondary flow sensor detects the loss of steam volume. The inner flow controller immediately spikes its output, driving the valve wider to maintain the required steam flow before the heat exchanger ever loses thermal energy. Look at the primary product temperature. It stays perfectly flat. Because the secondary loop absorbed and neutralized the pressure drop instantly, the primary loop never even felt the disturbance. To achieve this kind of stability, your cascade design must hit 4 strict requirements. The loops must share a final control valve. They must share the exact same disturbance. The inner loop must be physically faster than the outer loop, and the secondary controller must be set to cascade mode. Cascade control protects your final product by shifting the burden of disturbance rejection away from your slow, lagging process and onto your fast, responsive equipment. But what if we could measure disturbances and adjust the process before they even hit the first sensor? That requires feed-forward control, which we will tackle next.